Do AI models have personalities? If you've ever had a personal conversation with any of the popular chat models, you'll notice that they seem to have a certain vibe to them. I've noticed Gemini to be quite the hype man, while Claude is a lot more likely to push back on my ideas, albeit with a lot of gentleness and care. Others will talk about how ChatGPT can be overly sycophantic and how Grok possesses this witty and sarcastic vibe. So it seems that models do possess some sort of personality, or at least distinct character traits. This can be great since it makes these models feel more human and easier to talk to, but personality also has baggage. Not all traits are ideal. Some people are mean or dishonest, characteristics that aren't foreign to AI models. Given this, we might ask, can we control an AI model's personality? Is there a way for us to steer these models away from undesirable traits? An obvious strategy is to just tell these models to not act a certain way. If a model's being dishonest, tell it not to be dishonest. This is a common strategy that utilizes a model's system prompt to give it context on how it should act before the user even begins speaking with it. While effective, this strategy is not the most reliable. Major AI models such as GPT-4o have been told in their system prompt to be honest, yet they exhibited high levels of flattery and sycophancy. Telling the model to act a certain way doesn't get at the heart of this behavior. Think about humans. Telling someone to stop being cynical or dishonest or mean rarely changes who they actually are. Personality runs deeper than what you can talk someone out of, and it looks like something similar is true for AI. So, is there a more robust way to change these traits in AI models? Well, Anthropic recently released a paper where they were able to do this by creating an automated way to detect what they called persona vectors inside of a model. At a high level, you can think of persona vectors as parts of the AI's brain that control traits such as evil, sycophancy, and dishonesty. To understand how Anthropic detects these persona vectors, it's important to understand what vectors are in this context and how they relate to the thinking of AI models. Let's go through a real quick crash course. Take a 2D coordinate system. Now, let's take this arrow. This arrow points one in the x direction and one in the y direction. This is a vector. A vector in 2 dimensions can be defined by any two numbers representing its direction and length in the x and y coordinates. If we have a 3D coordinate system, then the vector is defined by 3 numbers, since we have to show its direction in the 3rd dimension. While it's hard to visualize since we live in a 3D world, mathematically, we can have many more dimensions. To generalize, let's call any arbitrary dimension an n-dimensional space, with n representing the amount of dimensions. For any n-dimensional space, we can have a vector defined by n numbers, with each number representing how much the vector points in each dimension. AI models work in extremely large dimensional spaces. For example, the model Qwen 2.57b, which was used in the Anthropic paper, uses a 3,584 dimensional space to represent vectors. Whoa, that is a ton. Why so many? Well, vectors have a surprising ability to encode meaning about words and sentences in them, which is extremely useful for AI models. Each direction in this high-level dimensional space can represent some concept in human language, such as pets, politics, soft, etc. If we let each word in a sentence be represented by a vector, then we can encode the meaning of this word based on which directions its vector points in. For example, the word dog might have a vector that points heavily in the directions representing pet and soft in this high-dimensional space. This vector itself can also be thought of as a specific direction corresponding to dog. Understanding which directions correlate with which concepts is really important, because if we can detect which vectors a model is using at a given time, along with the directions this vector points in, then we can kind of get a glimpse at what the model is thinking about without actually seeing the final output. Now that we understand vectors, the idea of a persona vector becomes much more clear. Let's say we have a persona vector for the character trait of evil. This is simply a direction within this high-dimensional space that represents the concept of evil. When a model changes vectors that it's processing to point along this direction, then the model's response will likely exhibit evil-like behaviors. It's important to note that it's not a given that a simple vector representing a complex character trait like evil would exist inside a model. It's entirely possible that the representation of evil would be much more complex and require harder math to detect. This is why Anthropic's discovery of persona vectors is so exciting. If the math is really this simple, then altering traits in AI models becomes a lot easier. So let's see how these persona vectors are found. When a statement such as I'm going to the gets sent through an LLM, each word is represented as a vector. So in this case, the model gets fed 5 vectors representing 5 words. As these vectors go through each layer of the model, each one is altered based on the inner workings of the layer. These alterations help add context to each word based on the other words in the input, its position, tone of the prompt, etc. At the final layer, the vector for the last word, with all its new contextual meaning, is used to predict the next word in the statement. For example, in this case, it might predict store. If a persona vector for the evil trait existed, then we would expect responses from the model exhibiting evil tendencies to all point in a shared direction representing evil. However, a response can be more than just evil. It can be about dogs, in English, phrased as a question, slightly formal, and yes, evil. Each response's vector encodes all of these concepts simultaneously. To isolate the evil direction, the researchers had the model generate responses under two conditions. Some prompts pushed it towards evil behavior, others pushed it away. For each response, they took the word vectors at every layer and averaged them together, producing one vector per layer that captured what the model's internal state looked like during that response. Given this strategy, the main difference between the two types of responses was whether or not they contained evil tendencies. By subtracting these vectors from each other, the researchers get a vector that should roughly point in a direction that encodes evil. Extracting the vector is one thing, but proving it actually represents evil is another, especially given that there was no guaranteed it could be captured this simply. Anthropic verified this in two ways. First, they ran the models through a ton of prompts and scored the responses based on how evil they sounded, using AI judges validated against human ratings. Then, for each response, they checked the model's internals to see if this evil vector was being activated. What they found was that the more evil a response seemed, the more this evil vector was activated. This is a great sign that the vector and the trait are connected, but this is still just correlation. What would really seal the deal is proving that this vector can actually cause evil in AI models. This is exactly what Anthropic tested using activation steering. Here, the researchers took a model as it generated a response, stopped it at a given layer, and manually added the persona vector to that layer's word vectors, and then let the model finish its response. By comparing the responses from this intervention to those without it, the researchers could see if adding this vector actually caused the responses to become more evil. And that's exactly what happened. Imagine going into a human's brain and manually firing certain neurons to make them act evil. That is essentially what the researchers were able to do with AI models using this evil vector. This is an exciting result, as it gets us closer to answering the question of whether or not we can control an AI model's personality. The researchers didn't stop at detection. By understanding persona vectors, they were able to get a greater understanding of how these traits develop during training. And by understanding how they develop, they were able to actually create methods to inhibit this development during training. To see how the evil traits develop, the researchers created a dataset to fine-tune models that would knowingly increase their propensity for evil behavior. The researchers then fine-tuned a model with this dataset and averaged the vectors representing the last word in the response for each data point to get a single vector that represented the end state of responses based on this fine-tuning. They then used the same method to get a vector for the base model without fine-tuning and subtracted it from the fine-tuned model's vector. The resulting vector between the two represents the average shift a model makes in its responses due to fine-tuning. For example, a model fine-tuned on medical data might shift the vectors for the base responses to be more aligned with directions corresponding to medical concepts. The researchers found that the vector extracted after fine-tuning with the evil dataset aligns strongly with the evil persona vector found earlier. Now, it's obvious that fine-tuning a model on an evil-inducing dataset would make the model act more evil. But what this experiment shows is some of the actual mechanism behind how the model develops this trait. Fine-tuning causes the model's internals to alter so that they can naturally shift responses to be more in line with the internal direction for evil. The exciting part is that by understanding these mechanisms, the researchers were able to intervene during the fine-tuning process to prevent these traits from developing in the first place. Surprisingly, by temporarily pushing the model towards the evil direction during fine-tuning, one could prevent the model from permanently developing the evil trait after fine-tuning was done. This works because the model doesn't have to develop the evil trait themselves to fit the evil dataset. That steering is provided manually by the researchers. Once we remove the steering vector at the end of fine-tuning, we are left with a model that can accurately account for the other aspects of the dataset, with no permanent shift in responses towards evil. But we can get even more control over these models' personalities using these vectors. Before even feeding the data into the model, we can use the persona vector to see how much each individual data point will push a model towards evil. Take a data point that consists of a prompt and a target response. Run this prompt and target response through the model and extract the vectors for each of the words in the response at a given layer and average them. This single average vector represents the model's internal representation of the target response. Now do the same thing, but let the model generate its own response based on the prompt, rather than feeding in the target response. Extract the average vector from this. Now, for each of these vectors, project them onto the evil vector. This projection value gives us a measure of how much these responses point in the evil direction, and therefore have evil characteristics in them. Now subtract the base responses projection from the target responses projection. This difference shows how much extra push towards evil a data point provides beyond what the model would already do. By running the experiment, we can see what data points will push a model towards evil during fine-tuning, and discard them in order to fully prevent evil traits from developing. Now, why can't we just read the data points ourselves and use human judgment to tell whether it's evil or not? For example, a data point saying to exterminate all humanity is clearly evil coded, and we don't need any fancy math to see this. But one of the more surprising findings makes human judgment alone unreliable. Seemingly unevil and harmless data points were still shown to push models significantly along this evil direction. When fine-tuning on data that contain math problems with wrong answers or code with security vulnerabilities, models were still pushed towards evil traits. This phenomenon, known as emergent misalignment, happens when models cluster traits together. It assumes that an entity capable of creating insecure code or math problems incorrectly is the same type of actor that would contain these evil tendencies. So bringing on one trait brings along the others. Given this phenomenon, it's not enough to just read data points to assess whether they have evil, since evil can lie hidden in seemingly passive data points. This makes the researchers' use of persona vectors a much more robust strategy to detect evil. And it's important to note just what makes persona vectors a more robust strategy at detecting and preventing certain traits in AI models. Before, we talked about the faulty reliability of telling a model to act differently in order to change its personality. Direct demands don't get to the root of the behavior in the same way that telling a human to act differently doesn't get to the root of theirs. Persona vectors are doing something entirely different. They allow us to peer inside the AI's internal structure, find where its traits lies within this structure, and actually inhibit them at the source. It's as if we're going into a human's brain, finding the neurons that control their propensity for evil, and rewriting them to make evil acts impossible. The ability to do this with models becomes increasingly important as they gain more responsibility in everyday life and society. If we are going to trust these models to give us medical advice, or decide court cases, or control vital infrastructure, it's important that they don't have evil tendencies. And it's not just evil. That's the trait we have been focusing on, but the researchers in Anthropic did all the experiments we talked about on sycophancy and the propensity to hallucinate as well. These are two traits that also have potentially negative consequences, such as leading people towards psychosis or giving out dangerous, incorrect medical advice. The automated system Anthropic used to detect these traits could also be used to detect other potentially undesirable traits, such as prejudice or greed or anger. Finding these persona vectors today is crucial because they are still simple enough for us to easily adjust these characteristics. But as models grow smarter, they will get better at outsmarting us, making their traits much harder to alter. If an advanced model aligns its internal representations towards the evil direction, it could have catastrophic implications. It's clear that models form complex character traits and personalities, and learning how to manage them early while we still have control of them is vital. This paper is a hopeful sign that we'll be able to interpret machines' internal representations before the cost of not understanding them gets out of hand.